Okay, here's some stuff about Bayes' theorem, sort of in a nutshell, but we'll start with a couple of definitions. The basic definition for conditional probability is the probability of A given B is equal to the probability of A and B, or A intersect B, over the probability of B for B not equal to 0. Okay, so if I multiply both sides by the probability of B, I can write this as the probability of A given, the probability of A and B is equal to the probability of B times the probability of A given B. Okay. So if I have two distinct possibilities or partitions of B, we can write this as the probability of A is equal to the probability of A intersect B plus the probability of A intersect B prime, or you might know it as B complement. It's the same thing. So these are mutually exclusive events. So now I can plug back in using my definition from the previous line. I can write this as the probability of B times the probability of A given B plus the probability of B complement times the probability of A given B complement. And that's just your law of total probability. Okay? So if we take this and write it in terms of Bayes' theorem, we now have the probability of B given A is equal to the probability of B times the probability of A given B all over that total probability of A. So when we have a problem, what we do is solve for that probability of A first, then we plug back into Bayes' theorem. So we're going to look at a couple of examples. In a certain state, 25% of all cars emit excessive amounts of pollutants. The probability is 0.99 that a car which emits excessive amounts of pollutants will fail the state emission test, and the probability that a car does not emit excessive amounts will still fail the test is 0.17. What is the probability that a car which fails the test actually emits excessive amounts of pollutants? Okay. So what I did here, I said, all right, I'm going to let E be excessive amounts and F be failing the test. So I know from the story, I have the probability of E is equal to 0.25. The probability of not excessive amounts is 1 minus that 0.25, which gives me 0.75. So I've got two distinct partitions, excessive, non-excessive. So then I have the probability that I fail the test given that I have excessive amounts is 0.99. The probability of failing given not excessive amounts is 0.17. And again, that's all just from the story. So now I want to get the probability of failing the test. So that's going to be the probability of E times the probability of F given E plus the probability of E complement times the probability of F given E complement. So now we just plug our numbers in. I have the probability of E, which is 0.25, times 0.99 plus 0.75 times 0.17. So I add those together, and that gives me 0.3750. So that's the probability of failure. That's the total probability. Now I want to find the probability of excessive amounts given that it failed the test. So that's the probability of E times the probability of F given E, which is actually the first term here, all over the probability of failure. So that's your 2475 over 0.3750, and that gives me 0.66. And that's all there is to it. Okay, but let's do some more. What if I have multiple partitions? Okay, so I've got B, and I'm going to slice A up into a bunch of little mutually exclusive pieces. I can write my total probability as the summation of I going from 1 to k of the probability of b sub I times the probability of A given b sub I. So let's take a look at another example and see what happens when we have those multiple partitions. So the members of a consulting firm rent cars from 3 different rental agencies. They get 60% from agency 1, 30% from agency 2, and 10% from agency 3. 9% of the cars from agency 1 need a tune-up, 20% of the cars from agency 2 need a tune-up, and 6% of the cars from agency 3 need a tune-up. What is the probability that a particular rental car needs a tune-up? And if a rental car needs a tune-up, what is the probability that it came from agency 2? So in part A, I really want the law of total probability. I want to find the probability that any particular car needs a tune-up. So let's lay out what we know just given from the story. So we have the probability of A1 is 0.6, A2 is 0.3, and A3 is 0.1. So those are our three partitions. I have the probability of probability of tune-up given A1 is 0.06. Probability of tune-up given agency 2 is 0.20. And the probability of tune-up given agency 3 is 0.06. So the probability of a tune-up, the total probability, is probability of A1 times probability of T given A1 plus probability of A2 times probability of T given A2 plus probability of A3 times probability of T given A3. So when I do that, that's going to give me my total probability of a tune-up. So I plug in my numbers. I have 0.6 times 0.09 plus 0.3 times 0.2 plus 0.1 times 0.06, and I get 0.054 plus 0.06 plus 0.006. When I add them up, that gives me 0.12. So the probability that any particular car needs a tune-up is 0.12 or 12%. So then we use this to get our Bayes theorem. So the probability of A2 given T is the probability of A2 times the probability of T given A2. So that's your second piece from the previous formula up here, all over the probability of a tune-up. So that's going to be your 0.06 all over the total of 0.12, and that's going to give me the probability of 0.5. Okay? Now let's just do one more just because it's fun. So we're going to go to an electronics plant, and we know that a new worker who completed training will meet the quota is 0.84. We also know that a new worker who did not complete the training but will still meet the production quota is 0.49. 70% of new workers complete training. What is the probability that a new worker will meet quota? And what is the probability, did I spell that wrong? I did. That's all right. That a new worker completed training given that he or she met the quota? Okay. So one of the things, and this is just something that I always do if I've got a problem, I'm going to lay out the individual pieces like that from the story and then solve it step by step. So the probability of completing training is 0.7. The probability that a worker did not complete training is 1 minus that, or 0.3. The probability that the worker met the quota given that he or she completed training is 0.84. Probability of meeting quota, not completing training, is 0.49. So the probability of meeting quota is P of T times P Q given T plus P of T complement times probability of Q given T complement. So that's your 0.7 times 0.84 plus 0.3 times 0.49. I get 0.588 plus 0.147. So my total probability of meeting quota is 0.735. Now I want to find the probability that a worker completed training given that he met the quota. And that's your first term from the previous equation all over the total probability of meeting quota. So that's your 588 over 0.735, and that comes out to be 0.8. Okay, I hope this helps. Bye.